Welcome to today's session on Fundamentals of Engineering Physics. Today we are going to cover a topic of rotational motion, that is moment of inertia. The objectives of this session are: after going through this lecture, the students will be able to understand basic concepts of moment of inertia and its relation to rotational motion and distribution of mass. They will be able to calculate moment of inertia for different shapes and distribution of mass. They will be able to illustrate its application in engineering physics and everyday situations. They will be able to clarify the difference and similarity between mass and moment of inertia. The concept of moment of inertia is fundamental in the fields of physics and engineering, especially when dealing with rotational dynamics. It is one of the many mass properties that describes an object's stability and the forces needed to alter its motion. The knowledge of moment of inertia about different axes is vital in determining how a device can hold up to external and internal forces. We will explore today the definition, related concepts, mathematical formulation, physical significance, examples, and finally applications in various domains. This lecture aims to provide a comprehensive understanding of moment of inertia, ensuring that the students are able to grasp both the theoretical and practical aspects. Going through the introduction, if we try to rotate a stick about various axes by turning our wrist, then it is observed that less effort is required to rotate the stick about an axis along its length. Also, more effort is required when we try to rotate the stick about an axis perpendicular to its length. The difference occurs because rotational inertia is different in the two cases. Unlike mass of an object, in translational inertia, which has only a single value, the rotational inertia of an object varies with the choice of different axes of rotation. It depends on the distribution of mass relative to the axis of rotation. As we can see in figure 1a above, the mass lies close to the axis of rotation, whereas in figure 1b, the mass lies much farther from the axis of rotation. This difference results in a larger rotational inertia in figure 1b, which is due to greater resistance to rotation. As the name suggests, moment means rotation and inertia is the resistance to this motion. So, resistance to rotational motion is expressed by a physical quantity known as the moment of inertia. Before starting today's topic, let us go through some important terms of rotational motion which will be helpful in describing our today's topic. Center of mass and center of gravity. The center of mass of a rigid body is a point whose position is fixed with respect to body as a whole. This point may or may not be within the body. It depends on the shape of the body and distribution of mass in the body. For symmetrical rigid bodies having uniform distribution of mass, the center of mass at the geometrical center, example, long thin rod of uniform cross section, or a thin circular ring, or a flat circular disc, rectangle, a sphere, cube and cylinder. For irregular shaped rigid bodies and having non-uniform mass, the distribution integral calculus is used to calculate center of mass. The center of mass is a point at which mass distribution is equal in all directions and it does not depend on the gravitational field. The center of gravity is a point in an object where the distribution of weight is equal in all directions and it does depend on the gravitational field. The center of gravity affects the stability of objects. The lower the center of gravity G is, the more stable the object. The higher it is, the more likely the object is to topple over if it is pushed. For ordinary bodies, the center of mass and the center of gravity coincide with each other. However, for larger bodies, it may not coincide. The next definition which we will review today is the torque. Torque is the tendency of a force that tends to cause rotation. Force causes an object to accelerate in linear motion. Similarly, in rotational motion, torque causes angular acceleration. Hence, torque can be defined as the rotational equivalent of linear force. In simple terms, it can be defined as the moment of force. Torque can be either static or dynamic. Static torque is a torque that does not produce an angular acceleration. Mathematically, torque can be represented as tau equals to F r sin theta, where r is the length of the lever arm and theta is the angle between the force vector and the lever arm. As we can see from the figure, the lever arm and the force vector are clearly indicated, either its center of mass or a given axis depending on the relevant application. It is actually the perpendicular distance from the point mass to the axis of rotation. The next definition which we are going to study is the radius of gyration. Radius of gyration is the distance from the center of mass of a body at which the whole mass could be concentrated without changing its moment of rotational inertia about an axis through the center of mass. Mathematically, the radius of gyration is the root mean square distance of the object's parts from either its center of mass or a given axis depending on the relevant application. It is actually the perpendicular distance from point mass to the axis of rotation. The radius of gyration about a given axis rg can be calculated in terms of the mass moment of inertia around that axis and the total mass m, which is a scalar and is not the moment of inertia tensor. Rg, that is radius of gyration about any axis, is given by under root of moment of inertia about that axis divided by mass. The next definition which we will review today is the principal axis. Principal axis of moment of inertia is the axis passing through centroid or center of gravity of the body. Figure shows the coordinate system with three principal axes of inertia. The origin of the coordinates is the center of mass. The main axis, that is the z axis, is determined as the principal axis with the smallest moment of inertia, and the x axis is the principal axis with the largest moment of inertia. The moment of inertia of a figure about a line is the sum of the products formed by multiplying the magnitude of each element of area or of mass by the square of its distance from the line. So, the moment of inertia of a figure is the sum of the moments of inertia of its parts. Now, we know that the moment of inertia of a figure about the lines which intersect at a common point are generally unequal. The moment is greatest about one line and least about another line perpendicular to the first one. A set of three orthogonal lines consisting of these two and a line perpendicular to both are the principal axis of inertia of the figure relative to that point. If the point is the figure's centroid, the axes are the central principal axis of inertia. The moments of inertia about principal axis are the principal moments of inertia. Principal moment of inertia is a quantitative measure of the rotational inertia of a body, that is, the opposition that the body exhibits to having its speed of rotation about an axis altered by the application of torque. The axis may be internal or external and may or may not be fixed. Now, coming to the definition of moment of inertia. The moment of inertia, often denoted by capital I, is a physical property of a rotating object that quantifies its resistance to rotational motion about a given axis. It is analogous to mass in linear motion and plays a crucial role in rotational dynamics. The moment of inertia is a scalar quantity. For linear momentum, the momentum small p is equal to mass times the velocity, whereas the angular momentum in rotational motion is equal to the moment of inertia I times the angular velocity. Now, if we consider the unit of moment of inertia, it is a composite unit of measure. In the international system, mass is expressed in kilograms and r in meters, with I, that is moment of inertia, having the dimensions of kilogram meter square. Now, if we compare rotational motion and linear motion, then we consider a mass m placed on a rod of length r and negligible mass, and which is constrained to rotate about a fixed axis. If the mass is released from a horizontal orientation, it can be described either in terms of force and acceleration with Newton's second law for linear motion, or as a pure rotation about the axis with Newton's second law for rotation. This provides a setting for comparing linear and rotational quantities for the same system. This process leads to the expression for moment of inertia of a point mass. In rotational motion, the angular displacement theta is analogous to displacement s in linear motion. Similarly, angular velocity in rotational motion is similar to v in linear motion. Also, angular acceleration alpha is analogous to acceleration a in linear motion. The quantity torque in rotational motion is analogous to force F in linear motion. In linear motion, we express force as the product of mass and acceleration. If we multiply both the sides of this equation by r, we can formulate the formula for moment of inertia. As you can see, the linear acceleration A is given by r times of angular acceleration alpha. Therefore, we can substitute in place of A r alpha and we get the expression I equals to mass times of radius square. Now, coming to the physical significance of moment of inertia. The moment of inertia is a measure of an object's resistance to change in its rotational motion. A larger moment of inertia indicates that more torque is required to achieve a given acceleration. This property is crucial in understanding the dynamics of rotating systems. From simple mechanical devices to complex structures like space stations. If a system is considered to be a collection of discrete particles, then the moment of inertia can be calculated using the equation I equals to summation I mi times Ri square, where mi is the mass of the ith particle and Ri is its perpendicular distance from the given line as shown in the figure. Mathematically, the moment of inertia I about a given axis is defined as the sum of the products of mass of each particle in the object and the square of its perpendicular distance to the axis of rotation. Now, if we wish to calculate moment of inertia of a continuous mass distribution, then it is found by using the integration technique. If the system is divided into an infinitesimal element of mass dm and if x is the distance from the mass element to the axis of rotation, then moment of inertia is given by I equals to integral of r square times of dm. The moment of inertia of an object depends on its mass distribution and the axis of rotation. These are the two factors on which moment of inertia depends. It is expressed by the integral as we have seen I equals to integral of r square dm, where I is the moment of inertia, r is the perpendicular distance and dm represents the infinitesimal mass element. For simpler shapes or uniform objects, the moment of inertia can be calculated using specific formulas derived from integration or geometric considerations. The moment of inertia of any body with a mathematically indescribable shape, the moment of inertia can be obtained by experiment. One of the experimental procedures employs the relation between the period, that is time, of oscillation of a torsion pendulum and the moment of inertia of the suspended mass. Now, we will go through some properties of moment of inertia. The first property is dependence on mass distribution. The moment of inertia depends not only on the mass of an object, but also on how that mass is distributed relative to the axis of rotation. Objects with more mass distributed farther from the axis of rotation have larger moments of inertia. The second property is the property of additivity. The total moment of inertia of a system of objects rotating about a common axis is the sum of the moments of inertia of the individual objects. This property allows for the calculation of moment of inertia of complex systems by adding the contributions of their components. The third property is the parallel axis theorem. This theorem states that the moment of inertia of an object about any axis parallel to an axis through its center of mass. As you can see from the figure, the axis passing through the center of mass has been marked as ICM, and the moment of inertia about the other axis can be represented by I equals to moment of inertia about the center of mass plus m times of square of the distance between the axis and the center of mass. The moment of inertia about the center of mass is indicated by ICM as we have seen from the figure, and ICM plus md square, that is mass and the square of the perpendicular distance between the two axes, gives the required moment of inertia. This next property is the perpendicular axis theorem. For any plane body, the moment of inertia about any of its axes which are perpendicular to the plane is equal to the sum of the moment of inertia about any two perpendicular axes in the plane of the body which intersects the first axis in the plane. As we can see from the figure, moment of inertia about any axis iz can be represented in terms of other two axes, that is IA and IB. Next property is the rotation axis. The choice of rotation axis can significantly affect the moment of inertia. For example, objects rotating about the axis passing through their center of mass often have simpler moments of inertia than those rotating about other axes. The density of the material, yet another property of moment of inertia. The moment of inertia is directly proportional to the density. Moment of inertia is equal to the product of mass and the square of the distance from the rotating axis to the tip of the rotating object. As we know, mass is directly proportional to density and moment of inertia both. Next property is the shape and size of the body. The moment of inertia is dependent on the rotational axis. The rotational axis of a body depends on the size and shape of the body. As the size and shape alter, the body's rotational axis also alters. This causes a change in the moment of inertia of the body. Let us now see how the moment of inertia changes with the choice of axis. Consider a uniform thin rod which is having uniform density and shape of mass capital M and length small l. We want a thin rod so that we can assume the cross sectional area of the rod as small and the rod can be thought of as a string of masses along a one-dimensional straight line. In this example, the axis of rotation is perpendicular to the rod and passes through the midpoint for simplicity. Our task is to calculate the moment of inertia about this axis. We orient the axis so that z axis is the axis of rotation and the x axis passing through the length of the rod. In this case, the moment of inertia comes out to be 1/12 of mass times the length of the rod square, that is 1/12 ml square. Next, we calculate the moment of inertia for the same uniform rod, but with a different axis choice. So, we can compare the results. We would expect the moment of inertia to be smaller about an axis through the center of mass than the end point axis. As you can see from the figure, if we chose the axis along the end point, the moment of inertia comes out to be 1/3 of ml square. This happens because more mass is distributed farther from the axis of rotation. Similarly, we can calculate for the rectangular object. As we can see, there are two figures, one representing a rectangular object and the other representing a rectangular plate. But here we see in both the cases the moment of inertia is same, that is 1/12 of mass times height square plus width square. This result is independent of the thickness of the plate. We will get the same result for a stack of plates of total mass m. Also, the same result is obtained for solid rectangular block of same dimensions. The moment of inertia, if we calculate for solid sphere, it is always less as compared to hollow sphere. As we can see from the figure, for a solid sphere, the moment of inertia comes out to be 2/5 of mr square, and for a hollow sphere it comes out to be 2/3 of mr square. Reason, the distribution of mass. Similarly, we can go through other examples, like if we consider a hoop and calculate its moment of inertia about the diameter, it comes out to be half of mr square. And if we calculate the moment of inertia of the same hoop about the cylindrical axis, it comes out to be mr square. For cylinder, we can see along a symmetrical axis, the moment of inertia is given by half of mr square, and for the same cylinder along the central diameter, the moment of inertia comes out to be 1/4 of mr square plus 1/12 of ml square. Similarly, if we compare a disc with a ring, for disc the moment of inertia comes out to be half of mr square, and for a ring it comes out to be mr square. The moment of inertia is all about how hard it is to get something spinning or to stop it from spinning. It depends on how much stuff there is and how it spread out around the spinning axis. When you add more stuff to the spinning object or spread it out farther from the axis, the moment of inertia gets bigger and it becomes harder to spin or stop. On the other hand, if you take away the stuff or bring it closer to the axis, the moment of inertia gets smaller and it becomes easier to spin or stop. The moment of inertia is specific to each object and its shape, and it's different for every axis of rotation, as we have seen it through various examples. So, the moment of inertia is a crucial concept that helps us to understand how things move and interact in the world around us. Now, moving on to the applications of moment of inertia. Understanding the moment of inertia is crucial for analyzing and predicting the behavior of rotating systems and objects in both theoretical and practical contexts. Rotational motion. This is the first application of moment of inertia. Moment of inertia is essential in describing how objects rotate around a specific axis. It is analogous to mass in linear motion and affects how quickly an object accelerates or deaccelerates in rotation when a torque is applied. Next application is rotational kinetic energy. The moment of inertia appears in the formula for rotational kinetic energy, much like the mass in formula for linear kinetic energy. The rotational kinetic energy of an object is directly proportional to its moment of inertia. The moment of inertia is fundamental in rotational dynamics as it appears in the equations of rotational motion, such as Newton's second law for rotation, that is tau torque equals to I times of alpha, that is angular acceleration, and the rotational kinetic energy equation, which is kinetic energy equal to I times of square of the angular velocity divided by 2. Next application is angular acceleration. When a torque is applied to an object, its angular acceleration is inversely proportional to its moment of inertia. Objects with larger moment of inertia require more torque to achieve the same angular acceleration as objects with smaller moments of inertia. Moving on to next application, that is pendulums. The moment of inertia affects the period of oscillation of a physical pendulum. For example, a pendulum with a larger moment of inertia will have a longer period than one with a smaller moment of inertia. Next, rigid body dynamics. In problems involving the motion of rigid bodies, the moment of inertia is a fundamental property that determines how the body responds to external forces and torques. It has got an application in engineering and design as well. The moment of inertia is crucial in engineering and design applications, such as in the design of mechanical systems, vehicles and structures. Understanding the distribution of mass in these systems is essential for predicting their behavior under rotational motion. The heavy mass mounted on the shaft of an engine is known as flywheel. The high magnitude of the moment of inertia of the flywheel helps in storing a large amount of energy. Next application is in solid body rotation. In situations where entire objects or systems are rotating, the moment of inertia helps in analyzing and predicting the rotational motion, stability and energy considerations of the system. Moment of inertia has application in shipbuilding as well. Moment of inertia has a big impact on shipbuilding. A ship may sink by rolling, but a ship will never sink by pitching. The reason is the moment of inertia over pitching axis is significantly huge compared to that over rolling axis. If we consider the hollow and solid shaft of the same mass, the power transmitted by the hollow shaft will be more than the solid shaft, which is because the moment of inertia of the hollow shaft is more than the solid shaft. Overall, the moment of inertia is a fundamental concept in physics with broad applications in various fields, particularly in understanding and analyzing rotational motion and dynamics. Now, going through this lecture, now you are able to solve numericals as well. A small numerical, if 3 point masses M1, M2 and M3 are located at the vertices of an equilateral triangle of length A, then we can calculate the moment of inertia of the system about an axis along the altitude of the triangle passing through M1. So, in this case, the moment of inertia can be represented by M1 times of the distance of the first mass from the axis of rotation m1 r1 square. Similarly, for the second m2 r2 square and for the third m3 r3 square. As the distance of the first particle from the axis of rotation, that is r1 is 0, r2 is a by 2 and r3 is a by 2. Summing up, we get the total moment of inertia as a square by 4 times of m1 plus m2. Now, summarizing today's lecture, we can conclude with the note that moment of inertia is analogous to mass in linear motion and plays a crucial role in rotational dynamics. The moment of inertia of an object depends on its mass distribution and the axis of rotation. A larger moment of inertia indicates more torque to achieve given acceleration. Moment of inertia of continuous mass distribution is given by integral of r square dm, and for a discrete particle system it is given by summation of I mi ri square. The moment of inertia is a fundamental concept in physics with broad applications in various fields, particularly in understanding and analyzing rotational motion and dynamics. That is all for today. Thank you.